Who are you? What are you? How are you? When are you? Why are you? We'll look at what you're made of first. What are you made of? And we'll look at the physical components, because you are more than your physical attributes. You have a mind, you have ideas, interpersonal skills, etc. How did you get here? When did you get here? And why are you here? Why did you get here? And we'll look at why later on as well. So you're in a room, and there's a whole bunch of people there, and yet they don't seem to recognize you. It's almost as though you're invisible. You can't see you or hear you, or if they do, they dismiss you, like you've got nothing between your ears. They don't really see you or hear you. But you know that you have good opinions. You know that you're a dynamic person, that you have energy, and you should be heard and seen. You will know what you're made of, even if they can't see you or can't hear you, as they should. Well, what are you made of? You're made of 65% water. Water is a molecule with two hydrogen, two hydrogen and one one oxygen. You actually have more hydrogen atoms in you than any other atom, so you're mostly hydrogen. You have other atoms too, of course, like carbon, oxygen, phosphorus. Carbon is very important because it can combine with other atoms of other elements and itself to form large molecules. It's important for most living things, including yourself. But if you're made mostly of hydrogen, then maybe you shouldn't get mad when people ignore you, because you might explode. Hydrogen is very dynamic. That's why they don't use hydrogen in airships anymore. I think it was the Hindenburg or Heisenberg, Hindenburg, I think, airship that blew up, and it's used hydrogen, which is the lightest element. It contains only one proton and one electron. Now they use, excuse me, they use helium, which has two protons, two neutrons, and two electrons. The second lightest element. So don't get mad, keep calm, and but all you do, don't release your hydrogen, because you blow yourself up and the other people in the room as well. The molecules are made up of atoms. The atoms are made up of electrons surrounding a nucleus. The nucleus is made up of protons and neutrons. Normally, except with hydrogen, there's the same number of neutrons as protons and the same number of electrons as protons. But the size of the nucleus is to the size of the atom, as a speck of dust is to the size of a football field. So you are pretty well all space. You're virtually nothing at all. Maybe that's why you can't be recognized. You're 99.9999999% space. But if your atoms are made up of mostly space, and the atoms in the floor are made up of mostly space, why don't you just fall through the floor? I mean, gravity is keeping you on the earth, but why don't you, if you're all space and the floor's all space pretty well, why don't you just keep falling through? Well, are you a magician? Well, maybe, because you levitate above the floor, 1 angstrom unit. You never actually touch the floor. You don't touch anything. So what's keeping you then from falling through the floor? Well, the atoms in you are surrounded by negative electrons. The atoms in the floor are surrounded by negative electrons. Like charges repel. And what is that force called? The electromagnetic force. So that's what's keeping you from falling through the floor, or keeping you from walking through the wall, or pushing your fingers through your arm. Let the force be with you. Now, if you're mostly hydrogen, where does that hydrogen come from? How does it get it there? Well, until 1929, no one really knew. Then Hubble, looking through the largest telescope on Earth, at the Mount Wilson Observatory in Los Angeles, he saw that all the stars were going away from the Earth, or receding from the Earth. What's that mean? Well, that means that space itself is expanding. How did he know that? Well, light is both a particle, photon, and a wave. You can see that it's a wave by just holding your two fingers up close together, looking through them with one eye, and you see lines in between the two fingers. Those are called interference lines, caused when waves interfere with each other. Same when you throw two rocks in a pool, they'll form waves and interfere with each other. And Newton, back in the 1600s, saw that when you pass light through a prism, it breaks up into different colors, like the colors of the rainbow, going from red up to indigo, indigo being like purple. And each of those colors have a different frequency, or a different wavelength. The wavelength is the amount of the distance between the crests of the two waves. And the wavelength of red light is larger than the wavelength of indigo. So the frequency of red light is lower than the frequency of indigo. Now, sound is also propagated by a wave. So if you hear a train coming towards you, the waves are being squashed together. Therefore, the wavelength is less and the frequency is higher. When the train goes by you, the waves are being pulled apart. So the waves are larger, wavelength is larger, and the frequency is lower. So it goes from a high pitch to a low pitch, from a high frequency to a low frequency, and you hear the sound drop as the train goes by. Well, the same for light, because it's propagated by waves as well. So when the light is going away from you, it shifts from the high frequency to the low frequency, from the indigo to the red. It's called a red shift. And with a spectrometer, you can look at it and you see each color has a signature, so you can see that the light is shifting towards the red. So that's how you tell that the universe is expanding. If the universe is expanding, then it must have been smaller and smaller in the past. And seeing how fast it's expanding now, you can go back and extrapolate back, and you find out it's 13.8 billion years ago. And everything was very small and very hot, maybe the size of a atom. The whole universe. And going back to time equals zero, what does that mean? How can time not exist? And if time is equal to zero, what was there before time? These are questions that science cannot answer, at least definitively. For it to be a scientific fact, you have to have empirical evidence, observations, and You can't just say speculate or have a hypothesis. Before it can be a truth theory or a law or scientific fact, you have to have evidence, and all evidence has to comply with that law. If there's one piece of evidence that does not, or if there's no evidence at all, then you have to say it's not a true theory, or you have to modify it, scrap it, modify it, or you can say that it only applies under certain conditions or in certain areas. So though there may be some speculation of how the universe came to exist, there's really no concrete evidence. And also, usually, when you have a hypothesis and you want to say that it's a true theory or a law, you perform an experiment in a lab and have it corroborated by someone else as well. And no one has yet, as far as I know, created a universe in the lab. As far as we know, there's only the one universe. And if there's another universe, they haven't come back to tell us about it. So science does not really have a definitive answer of how the universe came about. As a matter of fact, Planck, back in the beginning of the 20th century, he said that time can't keep dividing time down. I mean, you can start off with 1 billion years, go to 100 years, go to 1 million years, go to a year, go to a month, a week, an hour, minute, second, microsecond, but you can't keep going down. When you get to 10 to the minus 43 seconds, that's 43 times, you can divide it no longer. That's the smallest unit of time that exists. I call it the Planck time. Now it's the time it takes light to travel 1 Planck length. So length can only be divided down so far into 1.6 times 10 to the minus 35. I'm not sure how he came up with that, by the way, but so really, before 10 to the minus 43, there was really quite a mystery. When you divide in mathematics, when you divide by a smaller and smaller number, you get larger and larger entity. And when you try to divide by 0, all hell breaks loose. Get what is called a singularity or infinity. When I say all hell breaks loose, you multiply infinity times 3 and you get infinity. You add 1 to infinity, you get infinity. So math breaks down. So maybe that's what happens at time equals 0. You have something infinite that creates something finite, something that starts, has a times equal to 0. Again, this is a mystery. And they say everything is then time. Everything starts off with all the forces and everything, the whole universe, all the energy, all the forces, as one. So there's a super force. You can say something omnipotent, if you like, until you get to the first Planck time. And then the force of gravity separates from the super force. Then the 10 to the minus 35 is a strong force. It separates from the super force. And at that time, the universe expands faster than the speed of light. Now, how can anything go faster than the speed of light? It's supposed to be the limit. 10 to the 10 centimeters per second. But it's not that something's going through space faster than the speed of light. Space itself is expanding faster than the speed of light. Speed of light is constant. You look at a planet coming towards you, the light coming from the planet towards you, and the planet going away from you, and you'll see it's the same. 10 to the 10th centimeters per second. And we think it's a period of inflation because at that time the universe was quite uniform. Like when you blow up a balloon, or you inflate a balloon, the surface becomes very smooth. Well, that's one reason, if you like, that they think that they went through that period of inflation. Then at 10 to the minus 12, you get the electromagnetic force separate from you. And also, you get what is called a weak force. Now, if you were in that room and nobody recognized you, well, you do radiate. You're a radiant person. Not very much, though. It would take several million years times the age of the universe, 13.8 billion years, for your atoms to irradiate away through a radioactive decay. And that's what the weak force does. Nevertheless, it's very important to you. Without it, you would die. Because it keeps the center of the Earth molten. And the center of the Earth is iron. And when the Earth rotates, it sets up an electromagnetic field or shield around the Earth. And that protects you from all harmful solar radiation coming and cosmic radiation from outer space. And solar radiation come from the moon, from the sun, coming down, and it could kill you. It also protects the atmosphere, stops the sun's radiation from blowing away the atmosphere. And you need the atmosphere, the oxygen, and so on, to breathe and live. It also burns up a lot of the comets, meteors, meteorites, asteroids that are in outer space from coming down and hitting you and causing a lot of problems. Yeah. It does let some through, but usually it burns most of them up, so there's hardly any big ones. But even big ones can come through sometimes. So the weak force, even though it's very weak, and you don't have that much of it, it's nevertheless very important for you. Let the force be with you. Now that time too, you get all the particles, and for every particle there's what is antiparticle. So for instance, for electron, there's a positron. For a quark, there's an antiquark. Now, I didn't mention, I don't think, that your protons are made up and neutrons are made up of quarks. If you're in the room, you may be feeling that's one of the days you have your up, down days. You have your ups and downs, right? Well, you are all up and down. You're made up of up and down quarks. Your protons and neutrons are made up of up and down quarks. The proton has 2 up and 1 down, and the neutron has 2 down and 1 up. An up quark has a charge of 2/3, and a down quark has a charge of -1/3. So 2 up and 1 down, plus 2/3, plus 2/3, minus 1/3, 1 proton. 2 down and 1 up, minus 1/3, minus 1/3, plus 2/3, or 0. There are also other quarks. There's 3 levels of quarks, pairs of quarks. Up and down, which you are. Charm and strange, and top and bottom. Now there is a theoretical particle theory which highlights everything, that everything is made of. For each of the quarks, there's a lepton. For the electromagnetic, for the up and down, it's the electron. For the charm and strange, it's the tau. I think it's the tau. And for the top and bottom, it's the mu. I may have those two mixed up. And there's the four forces: the force of gravity, the electromagnetic force, the weak force, and the force. Did I say gravity? Yes. Gravity, weak force, strong force, and electromagnetic force. And for each of those forces, what's called a boson. For instance, for the electromagnetic force, the boson is a photon or light. So when you hold two magnets together and try to push them together, two south poles or two north poles, they resist. And what's happening is the light is causing that photons are keeping them apart. Similarly, there's a boson for the up and down, and for the strong force and for the weak force. There was also another boson that they predicted with that it should be there. Higgs. Back in the early 20th centuries, said there should be another boson which gives mass to the other particles. And until I think it was 2012, they tried to find it, and they did find it then, and it's called the Higgs particle, or Higgs boson. So whenever you have a theory or hypothesis, and which predicts something, and which you eventually find it to be true, it leaves more credence to that particular theory. How did they know that? How do you know that all these particles? What experiment can they have? Figure out what all these particles are. Closest thing you can come to with the beginning of the universe is the Large Hadron Collider at CERN in Switzerland. It simulates the amount of heat and power that occurred after 10 to the minus 12 seconds. They take, it is a 27 loop underground containing superconductors, accelerate particles near the speed of light in one direction, and then another group of particles near the speed of light in the other direction, collide them to see what they're made of, just like in a rotor in a car roller derby. When you smash cars together, the parts fly off, right? Now, at first, it was such a zoo. They called it a particle zoo. But eventually, they came down to the theory that this particle theory that I just outlined there. Now, they had to increase the power before they could find the Higgs boson, but they could never find the graviton. The graviton is the boson, by the way, of the force of gravity. Needed another piece of equipment called the LIGO, which used interference of waves. And that was just a decade or so ago they found that, giving again more credence to their particle theory. They found, what it did is found gravitational waves, and therefore there must be something goes with it. The particle would be the graviton. So at 10 to the minus 12 seconds in, you get all your particles and antiparticles. And then at 1/10 of a second, you get your protons. At 1 second, what happens there is quite significant. In the first to second, then you have all these particles and antiparticles. And when a particle and an antiparticle come together, they annihilate each other, turn back into energy. And at 1 second, for every billion, some say 100 million, antiparticles, you get a billion or 100 million particles. And get one extra particle. That's important. Because you're made up of particles. You don't have any antiparticles, so you blow up again. You can't exist together with particles and antiparticles. So, you had 1 billion to 1 chance of getting through that. You can thank your lucky stars. You'll thank your lucky stars later on. But right now, you can thank your lucky something that you got through that first second. When I say that you have particles and energy that switch back and forth, well, before 1905, everybody thought no. Energy is one thing and matter is another. There's a law of conservation of matter, the law of conservation of energy. So they're two separate things. But then Einstein, with his special theory of relativity, said no, they're actually equal. E equal mc squared. Your energy is equal to your mass, or the amount of matter you have, or material you have, times the speed of light, times the speed of light. So again, if you're mad and you think you might want to explode in that room, don't do it. If you change your mass into energy, you not only blow yourself up, the room, the building, the city, and some of the surrounding territory. So keep calm. Don't blow up. But so far, we have not yet told you how you got your hydrogen. At the end of 1 second, then you have all these protons and photons and electrons swarming around. And it's still so hot and dense, they can't separate out. But after 380,000 years after that, it takes until it cools enough so that the electron can be captured by the proton. And what do you get when you have a proton and electron? You get your hydrogen. So that's where you got all the hydrogen in your body that you're over 50% made of, at least your atoms. So your hydrogen, and most of you, is 13.8 billion years minus 380,000 years. And you thought you were like less than 100 years. Well, most of you is that old. Where do you get your other atoms from? Where do you get your carbon, oxygen, phosphorus, and atoms of other trace elements? Well, get all that hydrogen being created, and over the next billion years or so, Gravity forces it all together into bigger and bigger balls, right? And it gets very hot at because of all the force of gravity, the center. And also the force of gravity overcomes the electromagnetic force that's trying to keep the space in between to keep things from touching. And what happens is that it takes the space out of your atoms, and they touch, or they fuse. And when they fuse together, they form hydrogen. So with hydrogen has two neutrons, two protons, and two electrons. But it also has extra energy or mass, same thing, left over. That's what you get when you get a hydrogen bomb. It explodes. So you have this force that's trying to force everything apart, and you have the force of gravity trying to keep everything, attract everything. And so you have a tug of war between fusion and the force of gravity. And what do you get? Judy Garland. A Star is Born. It's the closest star that you have towards you. You should know. Do you know the name? Well, it's the sun. The sun is a star, and it's up there converting hydrogen into helium and giving off light and warmth and energy. Now, a star which is over 10 times more massive than the sun, when it gets through converting all this hydrogen to helium, then it fuses helium and forms the next element in the periodic table, and so on, until it eventually forms carbon and oxygen. But when it gets up to iron, and iron is much heavier, it has more protons and neutrons, it can't fuse them together. It doesn't give off energy, it requires extra energy. So there's no energy keeping the force of gravity at bay. So the star collapses instantaneously, which much force, it blows itself up into what is called a supernova, spewing out all the materials and the elements into space. And it's so strong as well, so much force, it's able to fuse the iron atoms and all the most of the other elements in the periodic table, the heavier elements, most of them. But it leaves behind a core for all the atoms with the space squashed out of them, called a neutron star. And 1 teaspoon or tablespoon, I can't quite remember, would weigh more, and be more massive than all the mass of all the cars in North America. Now, don't quote me on that because I'm not too sure. I tried to test it out, experiment, but I gave up counting after a few hundred cars or so. And when I took some of the neutron star, I couldn't hold on to it. The force of gravity, because of so much mass, overcame the electromagnetic force, was keeping it, and it fell right through my hand and right through the floor and through the earth. Now, a star which is over 100 times more massive than our sun, when it explodes, leaves behind a black hole, something so massive that even light, photons of light, can't escape. So where does all that material then go? It goes into space after supernovas, and then the gravity takes over again, and you get a second generation star. Our star is a third or fourth generation. And it came about in the solar system 4.5 billion years ago. Some say 4.6 billion. And by the way, just to show you that the science, when you say it's a scientific fact, well, there can always be other evidence, or you can refine your findings when new evidence comes about. So, we used to say 10 years ago that the universe was 13.7 billion years. Now they must have found some more evidence, and they say it's 13.8 billion years. It used to be that they said that the solar system was 4.5 billion. Now they say 4.6 billion. So you can never be absolutely 100% sure about a scientific fact. There can always be more evidence that shows you have to modify it, scrap it, or say it only exists under certain conditions. Now, when the solar system formed, then the sun would have had the light element in the center, the hydrogen. The other elements would circle it. It was quite chaotic back then because everything was bumping into each other. And it would start off, say, with two particles, small particles, when using the electrostatic force to bring them together. And then gravity would, force of attraction, bring them together. And they would be colliding, breaking up. And gravity would again make them bigger and bigger, bring them together, make them bigger, till you get your planets. And there would probably be 100 planets. And some of the planets were even bashing into each other, demolishing each other. Earth was hit by a planet the size of Mars, and it didn't explode. But a lot of the material of the Earth was spewed off into space, circled the Earth, and formed our moon. Now, have you ever gone around the moon? You should take a trip around the moon, and you see there's one big black spot there. It's a lava lake. But then when you come around this side, you see a whole bunch of lava lakes. The man on the moon. Or if you look from the top to the bottom, you can see a man and a woman kissing. Maybe that's why it's considered to be so romantic. Well, why is that? Because the Earth's crust, the moon's crust on the other side is 27 kilometers thicker than the crust on this side. And why is that? Because when the moon was forming, it would be very close to the Earth, circling the Earth. And the Earth would have been molten because of all the bombardment from all the stuff from outer space. So it would have been very hot. And the moon would have materials going around it as well. And the other side of the moon would have been cooler, away from the molten Earth, and more material would have settled there. And that's why the moon's crust on the other side is larger, it's thicker than the crust on this side. Also, the astronauts brought back rocks which could only have been formed on the Earth. And the moon is very important for you because it stabilizes the Earth. And without that, complex life like yourself would probably not exist.